Have you ever heard whispers of a forgotten planet? One that once existed in our solar system, only to be shattered and scattered into oblivion? Between Mars and Jupiter, in the vast emptiness of space, lies a field of broken remnants, a cosmic graveyard known as the asteroid belt. But what if those rocks aren't just floating debris? What if they are all that's left of a once thriving planet? Let's rewind to the early 19th century. In 1801, an Italian astronomer named Giuseppe Piazzi made a groundbreaking discovery. He spotted a strange object orbiting the Sun between Mars and Jupiter. That object would later be named Ceres, and it was unlike anything previously catalogued. Just a year later, another astronomer, Heinrich Olbers, found a second body, Pallas, following a remarkably similar orbit. By 1807, two more celestial objects, Juno and Vesta, were discovered in that same region of space. It wasn't long before scientists began to piece together a tantalizing theory. These objects weren't just individual rocks. They could be the shattered remains of a planet that once existed between Mars and Jupiter. They even gave it a name, Phaeton, sometimes referred to as Phaeton in older texts. This idea became known as the disruption theory. According to it, a full-fledged planet once orbited peacefully in that region, but was later destroyed either by a violent impact or some internal cosmic catastrophe. So, what could have shattered an entire planet? One theory suggested a collision with a massive space object, perhaps a rogue asteroid or even a star. Another more speculative explanation involved Nemesis, a hypothetical red or brown dwarf star believed by some to be orbiting the Sun on a long elliptical path. If such a star existed and came close enough, its gravitational forces might have torn Phaeton apart. Others proposed that Jupiter, the solar system's behemoth, may have pulled Phaeton in too close, tearing it apart with its immense gravitational pull, just like it does with many comets that cross its path. But over time, the disruption theory fell out of favor. As our telescopes improved and our understanding of planetary formation evolved, a new explanation emerged: the accretion theory. According to this theory, the asteroid belt isn't the aftermath of a planet's destruction. It's the remains of a planet that never formed in the first place. Billions of years ago, the early solar system was a swirling disk of gas, dust, and rock fragments, a protoplanetary disk. In most regions, these fragments gradually clumped together under gravity, forming the planets we know today. But in the space between Mars and Jupiter, something interfered. That something was Jupiter. Jupiter's immense gravitational field prevented the material in that region from coalescing into a planet. Instead, the fragments kept colliding and breaking apart, resulting in the scattered rubble we see today, the asteroid belt. This belt lies between 2.1 and 3.3 astronomical units from the Sun and contains millions of rocky bodies. Yet despite the popular image from sci-fi movies, the belt is mostly empty space. The asteroids are so spread out that a spacecraft could pass through without ever coming close to a collision. Still, the largest four asteroids, Ceres, Vesta, Pallas, and Hygiea, comprise more than half of the belt's total mass. These space rocks are crucial to our understanding of planetary formation, as they hold clues to the early solar system preserved for over 4.5 billion years. Ceres, the largest of them all, is so massive that it's classified as a dwarf planet. It's roughly 940 kilometers in diameter and even shows signs of water ice, raising fascinating questions about the potential for life or prebiotic chemistry in such environments. In 1972, NASA's Pioneer 10 spacecraft was the first to traverse the asteroid belt. At the time, many feared it might be destroyed by the dense field of debris. But to the relief of mission controllers, it passed through unharmed, disproving the sci-fi image of a chaotic obstacle course. Since then, several other probes, including Galileo, Dawn, and Juno, have explored the region, each revealing more about this intriguing slice of space. What's even more fascinating is how these asteroids help us peer back in time. By studying their composition, whether carbonaceous, silicate, or metallic, we can understand the building blocks of planets. Some even carry organic molecules, perhaps the same that seeded life on Earth. But still, the mystery remains. Could it be that the disruption theory holds a grain of truth? That there once was a world called Phaeton, torn apart in a violent cosmic event? Or is the asteroid belt just a planet that almost was? Science is a moving frontier, always reshaping itself with new evidence. For now, both theories linger in scientific lore, each compelling, each echoing with the ghosts of a lost world. And that's just the beginning. Stay tuned for Segment 2, where we dive deeper into the largest asteroids, their role in the evolution of our solar system, and the continuing search for a possible Planet 9 hiding beyond Neptune. If you enjoyed this segment, don't forget to give it a thumbs up and subscribe to Infinity Beyond, your window to the wonders of the cosmos. Have you ever heard whispers of a forgotten planet? One that once existed in our solar system, only to be shattered and scattered into oblivion? Between Mars and Jupiter, in the vast emptiness of space, lies a field of broken remnants, a cosmic graveyard known as the asteroid belt. But what if those rocks aren't just floating debris? What if they are all that's left of a once thriving planet? Let's rewind to the early 19th century. In 1801, an Italian astronomer named Giuseppe Piazzi made a groundbreaking discovery. He spotted a strange object orbiting the Sun between Mars and Jupiter. That object would later be named Ceres, and it was unlike anything previously catalogued. Just a year later, another astronomer, Heinrich Olbers, found a second body, Pallas, following a remarkably similar orbit. By 1807, two more celestial objects, Juno and Vesta, were discovered in that same region of space. It wasn't long before scientists began to piece together a tantalizing theory. These objects weren't just individual rocks. They could be the shattered remains of a planet that once existed between Mars and Jupiter. They even gave it a name, Phaeton, sometimes referred to as Phaeton in older texts. This idea became known as the disruption theory. According to it, a full-fledged planet once orbited peacefully in that region, but was later destroyed either by a violent impact or some internal cosmic catastrophe. So, what could have shattered an entire planet? One theory suggested a collision with a massive space object, perhaps a rogue asteroid or even a star. Another more speculative explanation involved Nemesis, a hypothetical red or brown dwarf star believed by some to be orbiting the Sun on a long elliptical path. If such a star existed and came close enough, its gravitational forces might have torn Phaeton apart. Others proposed that Jupiter, the solar system's behemoth, may have pulled Phaeton in too close, tearing it apart with its immense gravitational pull, just like it does with many comets that cross its path. But over time, the disruption theory fell out of favor. As our telescopes improved and our understanding of planetary formation evolved, a new explanation emerged: the accretion theory. According to this theory, the asteroid belt isn't the aftermath of a planet's destruction. It's the remains of a planet that never formed in the first place. Billions of years ago, the early solar system was a swirling disk of gas, dust, and rock fragments, a protoplanetary disk. In most regions, these fragments gradually clumped together under gravity, forming the planets we know today. But in the space between Mars and Jupiter, something interfered. That something was Jupiter. Jupiter's immense gravitational field prevented the material in that region from coalescing into a planet. Instead, the fragments kept colliding and breaking apart, resulting in the scattered rubble we see today, the asteroid belt. This belt lies between 2.1 and 3.3 astronomical units from the Sun and contains millions of rocky bodies. Yet despite the popular image from sci-fi movies, the belt is mostly empty space. The asteroids are so spread out that a spacecraft could pass through without ever coming close to a collision. Still, the largest four asteroids, Ceres, Vesta, Pallas, and Hygiea, comprise more than half of the belt's total mass. These space rocks are crucial to our understanding of planetary formation, as they hold clues to the early solar system preserved for over 4.5 billion years. Ceres, the largest of them all, is so massive that it's classified as a dwarf planet. It's roughly 940 kilometers in diameter and even shows signs of water ice, raising fascinating questions about the potential for life or prebiotic chemistry in such environments. In 1972, NASA's Pioneer 10 spacecraft was the first to traverse the asteroid belt. At the time, many feared it might be destroyed by the dense field of debris. But to the relief of mission controllers, it passed through unharmed, disproving the sci-fi image of a chaotic obstacle course. Since then, several other probes, including Galileo, Dawn, and Juno, have explored the region, each revealing more about this intriguing slice of space. What's even more fascinating is how these asteroids help us peer back in time. By studying their composition, whether carbonaceous, silicate, or metallic, we can understand the building blocks of planets. Some even carry organic molecules, perhaps the same that seeded life on Earth. But still, the mystery remains. Could it be that the disruption theory holds a grain of truth? That there once was a world called Phaeton, torn apart in a violent cosmic event? Or is the asteroid belt just a planet that almost was? Science is a moving frontier, always reshaping itself with new evidence. For now, both theories linger in scientific lore, each compelling, each echoing with the ghosts of a lost world. And that's just the beginning. Stay tuned for Segment 2, where we dive deeper into the largest asteroids, their role in the evolution of our solar system, and the continuing search for a possible Planet 9 hiding beyond Neptune. If you enjoyed this segment, don't forget to give it a thumbs up and subscribe to Infinity Beyond, your window to the wonders of the cosmos. As we venture deeper into the mysteries of our solar system, the asteroid belt continues to raise profound questions. Is it truly just a graveyard of rocks that never became a planet? Or is it the last remnant of a once thriving world? An ancient planetary civilization, perhaps, now reduced to rubble and drifting silence. Let's revisit the four most massive bodies in the asteroid belt: Ceres, Vesta, Pallas, and Hygiea. These aren't just space debris. They are worlds in miniature, each one offering unique clues about our solar system's chaotic infancy. Ceres, as we learned earlier, is the crown jewel of the asteroid belt. At nearly 7 kilometers in diameter, it's large enough to be classified as a dwarf planet. What makes Ceres especially fascinating is the presence of bright spots on its surface. Detected by NASA's Dawn spacecraft, these spots are believed to be salt deposits, possibly left behind by briny water seeping from the interior. This hints at a radical possibility that Ceres once had, or may still have, a subsurface ocean. If confirmed, it could mean that even this distant icy rock has the conditions necessary for life. Not intelligent life, perhaps, but microbial ecosystems that may have persisted in the darkness for billions of years. Moving on to Vesta, we find a different kind of story. Vesta is much rockier, much brighter, and has a huge impact crater at its southern pole, Rhea Silvia, which is over 500 kilometers wide and 20 kilometers deep. That's nearly the size of the asteroid itself. This crater, and the debris blasted from it, are believed to have contributed to a class of meteorites known as Hyade meteorites, some of which have been found right here on Earth. So, in a way, you could be holding a piece of Vesta in your hand without ever knowing it. Pallas, the third largest asteroid, has a highly tilted orbit, making it harder to reach with current spacecraft. Yet what little we do know suggests it's a primordial survivor, composed of material unchanged since the formation of the solar system. Studying Pallas could be like reading a chapter from the universe's own diary. And then there's Hygeia, a dark and mysterious body that barely qualifies as spherical. Hygeia might have formed not through accretion like the others, but as a result of a violent collision, reshaping itself from the fragments. If that's true, then it could be the cosmic twin of the disruption theory itself, a visual metaphor for what could have happened to Phaeton. Each of these bodies carries its own scars, its own narrative, carved by time, collisions, and solar winds. Yet they all orbit in the same space, the asteroid belt. But what keeps this region so distinct, so oddly balanced between chaos and order? The answer lies once again in Jupiter. With a mass 2.5 times that of all the other planets combined, Jupiter's gravitational influence is immense. As the solar system formed, its presence disrupted the orbits of nearby protoplanets, sending some careening into the sun, others ejected into deep space, and some shattered entirely. It's not hard to imagine that a forming planet, Phaeton, as it was once named, tried to hold itself together in this turbulent zone. But as Jupiter grew and flexed its gravitational muscles, the young world could have been torn apart, leaving behind the fragments we now call asteroids. This raises an eerie parallel to what's known as the Roche limit, the minimum distance at which a celestial body can orbit another without being torn apart by tidal forces. Cross that line, and the planet doesn't just crumble. It explodes into a disk of orbiting debris. So maybe Phaeton didn't just fail to form. Maybe it succeeded, only to be torn limb from limb by Jupiter's gravity, like some ancient cosmic sacrifice. But if this lost world truly existed, could it have hosted life? Some scientists speculate that if Phaeton had a stable orbit for a long enough period before its destruction, it could have been geologically active, with volcanic systems, magnetic fields, and even oceans. Under such conditions, primitive life could have evolved, only to be annihilated in a cataclysmic event. We may never know, but as technology advances, we're not just observing asteroids, we're visiting them. In recent years, missions like Japan's Hayabusa and NASA's OSIRIS-REx have actually landed on asteroids, collected samples, and returned them to Earth. These rocks are time capsules, preserving the chemistry of the early solar system. And soon, we may apply these same techniques to bodies in the asteroid belt itself. One day, we might even build space stations or colonies within the asteroid belt. With proper shielding and infrastructure, Ceres or Vesta could become stepping stones to the outer solar system, a place for mining, science, or even habitation. Think about it. A world that failed to become a planet might one day become home to explorers from Earth. The irony is poetic, and the future limitless. But before we rush into tomorrow, we still have ancient puzzles to solve. Some astronomers believe that among the asteroids lies something more, a massive, undiscovered object with enough gravity to explain anomalies in the Kuiper Belt. This hypothetical body is known as Planet 9. Could it be hiding at the edge of the solar system? Or is it a phantom conjured by gravitational math? Whatever the truth, one thing is certain. The more we learn about the asteroids, the more they reveal the skeleton of a solar system in its infancy. They are not just debris. They are witnesses, and they have stories to tell. In the next episode of Infinity Beyond, we'll explore the strangest kinds of asteroids ever discovered, metallic monsters, tumbling twins, and ones that spin so fast they're on the verge of tearing themselves apart. Don't miss what's coming next, and if you haven't yet, subscribe to Infinity Beyond for weekly journeys through time, space, and the cosmic unknown. For centuries, humanity has looked to the skies trying to decipher the silent language of the stars. Among the many celestial mysteries, one of the most haunting remains. Was there once a planet between Mars and Jupiter that no longer exists? And if so, did Jupiter destroy it? Let's examine the evidence with an open mind and a scientific lens. We already know that the asteroid belt sits precisely in the zone where this mysterious planet, Phaethon, would have orbited. Some scientists in the 19th century were so convinced of this planet's prior existence that they named it in theory, long before space probes or high-resolution imaging were available. But with time and technology, the theory evolved, or rather, diverged. Modern astronomy largely supports the accretion theory, the idea that the asteroid belt represents a planet that never formed, its material thwarted by the gravitational influence of nearby Jupiter. However, this doesn't fully explain the orbital paths, the mass distribution, and the chemical diversity of the asteroids within the belt. Some asteroids are carbon-rich, others silicate-heavy, and some contain metals like nickel and iron in amounts usually found in planetary cores. How could such differentiation exist if no full-sized planetary body ever formed there? This is where the disruption theory re-emerges, with a vengeance. According to this idea, a planet did form in the early solar system and was later destroyed, either by an internal cataclysm or, more intriguingly, by Jupiter's massive gravitational forces. Jupiter is not just the largest planet in our solar system. It is a cosmic bully. Its gravitational reach is immense, capable of altering the orbits of moons, capturing comets, and flinging asteroids out of the belt entirely. In fact, some scientists call Jupiter the solar system's vacuum cleaner because of the way it clears debris. But what if Jupiter did more than just clean up? What if it tore apart a young planet that dared to form too close? The physics support this possibility. The region between Mars and Jupiter sits near the so-called Kirkwood gaps, areas in the asteroid belt where no asteroids are found. These gaps correspond to orbital resonances with Jupiter, meaning that any object orbiting there would receive regular gravitational nudges from the gas giant, nudges strong enough to destabilize its orbit over time. Imagine a young, newly formed planet, Phaethon, caught in these resonances. Each time it completes an orbit, Jupiter tugs on it slightly. Over millions of years, these tugs build up, like waves eroding a cliff. Eventually, Phaethon's orbit becomes so unstable that it either crashes into another object, is pulled toward the Sun, or is shattered completely. Such a scenario could explain the asteroid belt's fragmented composition, chunks of crust, mantle, and even core material drifting separately in space. It also aligns with impact evidence found in meteorites on Earth, some of which appear to have originated from large, differentiated bodies. Jupiter's role in shaping the solar system is complex. While it protected Earth by deflecting dangerous comets and asteroids, it may have also prevented another planet from forming or surviving. In this light, Jupiter is both a guardian and a destroyer. And what if this destruction wasn't a one-time event? New models suggest that the early solar system may have been far more violent than we once believed. Planets may have migrated, shifted positions, and even swapped orbits due to gravitational interactions. Jupiter itself may have moved inward before settling into its current orbit, bulldozing through planetesimals and disrupting any forming planets in its path. This chaotic reshuffling is known as the Grand Tack hypothesis, and it supports the idea that entire worlds could have been displaced or demolished by Jupiter's movement. But here's where things get even more fascinating. Some scientists believe that the asteroid belt might not be the only graveyard in our solar system. Closer to Earth, we find the main belt comets, icy bodies that orbit within the asteroid belt and occasionally release gas, much like comets from the outer solar system. These bodies blur the line between comets and asteroids, suggesting that the asteroid belt may have had icy, water-rich worlds. possibly with subsurface oceans, like those we suspect on Ceres. If true, then Phaeton might have been more than just rock and metal. It could have been a wet world, with oceans, clouds, even potential for life. And here's a question that keeps scientists up at night. If Phaeton had time to develop life, what happened to it when the planet was destroyed? Could microbial life have hitched a ride on fragments hurled into space? Could they have landed on Mars, or even Earth, carried via panspermia? The theory that life can travel across the universe on space rocks. While there's no hard proof yet, the idea is not far-fetched. Scientists have already proven that certain bacteria can survive the vacuum of space for years. If microbial life existed on Phaeton, it's not impossible that some of it could still be alive, sleeping in a rock waiting to be found. Think about that. Somewhere, drifting between Mars and Jupiter, could be a fossilized piece of an ancient living world. Maybe it's already landed on Earth. Maybe it's in a museum drawer labeled as just another meteorite. Or maybe it's waiting for us to find it. In the next segment, we'll explore how missions like OSIRIS-REx, Hayabusa 2, and Dawn are helping us unlock these mysteries by bringing back samples from asteroids, studying their composition, and possibly revealing the fingerprints of a lost planet. These missions are not just technological marvels, they are time machines, reaching into the past and pulling out secrets that have been frozen in rock for billions of years. So the question remains, did Jupiter destroy a planet in our solar system? Maybe it did. Maybe the evidence is floating in space right now. Or maybe, just maybe, it's already here, beneath our feet. Stay tuned to Infinity Beyond, where in our next episode, we'll unravel the secrets behind the spacecraft exploring asteroids, bringing home ancient relics of cosmic history, and perhaps answers to questions as old as time. And if you're enjoying this journey, don't forget to subscribe, like, and share. Let's explore the forgotten corners of our solar system together. What if we told you that the answers to the solar system's greatest mysteries aren't in distant galaxies, but drifting silently between Mars and Jupiter? These aren't just space rocks, they're time capsules, ancient messengers that have witnessed the birth of planets, the fury of collisions, and the fading light of forgotten worlds. And now, for the first time in human history, we've begun to reach out and bring those messengers home. Welcome to the new era of asteroid exploration. It all started with a question. What are asteroids really made of? Are they just dead debris? Or are they relics of a world that could have been? To answer that, we needed more than telescopes. We needed to go there. And so, missions like NASA's OSIRIS-REx, JAXA's Hayabusa and Hayabusa 2, and NASA's Dawn spacecraft were born. Their goal? To visit asteroids, touch them, sample them, and return with pieces of the early solar system locked in stone. Let's begin with OSIRIS-REx, one of the most ambitious missions in NASA's history. Launched in 2016, this spacecraft traveled over 200 million miles to reach Bennu, a near-Earth asteroid roughly 500 meters wide. But Bennu is no ordinary rock. It's ancient, older than Earth itself, formed in the first 10 million years of the solar system. What made Bennu particularly fascinating is that it's rich in carbonaceous material, the building blocks of life. Scientists hoped that by studying samples from Bennu, we might better understand how organic molecules arrived on Earth. In October 2020, OSIRIS-REx made history when it extended its robotic arm and performed a flawless touch-and-go maneuver, scooping up dust and rock from Bennu's surface. That sample is now en route to Earth, scheduled to arrive in a secure capsule. What secrets lie within it? No one knows. But whatever they are, they could redefine our understanding of how life began. Across the Pacific, the Japanese Aerospace Exploration Agency, JAXA, was running its own groundbreaking missions. In 2005, Hayabusa became the first spacecraft to land on an asteroid and return a sample to Earth. It visited Itokawa, a peanut-shaped asteroid made mostly of silicate rock, and though the mission faced technical setbacks, it succeeded in returning dust particles, enough to prove that direct sampling was possible. Then came Hayabusa 2, targeting the asteroid Ryugu, a larger, darker, and more primitive body. Launched in 2014, the mission arrived at Ryugu in 2018 and did something extraordinary. It fired a bullet into the asteroid's surface, collected samples, and even dropped a small impactor to blow a crater in the surface, exposing material untouched by radiation or micrometeorites for billions of years. The samples returned to Earth in 2020 and are now being analyzed. Early results have shown evidence of water-bearing minerals, further supporting the idea that asteroids may have delivered water and life's ingredients to early Earth. But the story doesn't stop there. NASA's Dawn mission took a different approach. Instead of returning samples, Dawn became the first spacecraft to orbit two extraterrestrial bodies, Vesta and Ceres, the largest members of the asteroid belt. At Vesta, Dawn captured images of massive impact craters, canyons, and mysterious grooves that circled the asteroid's equator. It revealed that Vesta is differentiated, meaning it once had a molten core, just like Earth. That suggests Vesta nearly became a full-fledged planet, but was stopped short, likely by Jupiter's gravitational interference. Then Dawn traveled to Ceres, where it discovered bright spots inside craters. These turned out to be salt deposits, hinting at briny water beneath the surface. Ceres, it turns out, might be geologically active even today, another candidate for harboring microbial life in underground oceans. What all these missions reveal is that asteroids are not just relics of destruction. They are repositories of creation. They tell a story far older than humanity, a story written in dust and rock, a story of heat and pressure, of impacts and chemistry, of time so deep we can scarcely grasp it. And perhaps most importantly, these missions are helping us answer one of the most profound questions of all. How did life begin? If carbon-rich asteroids like Bennu contain amino acids or precursors to RNA, it supports the theory that life didn't start on Earth. It arrived here, seeded by cosmic messengers from deep space. This theory, known as panspermia, is no longer science fiction. It's being tested in laboratories right now using real samples from real asteroids. Think about that. We are touching the origins of life. But asteroid missions aren't just about the past. They're also about the future. Asteroids may one day become resource hubs, supplying rare metals, water, and even fuel for deep space missions. Mining asteroids could reduce the need for costly launches from Earth and allow long-term survival in space. Companies like Planetary Resources and Asteroid Mining Corporation are already researching how to harvest materials from near-Earth asteroids. Some even dream of building habitats inside hollowed-out asteroids, shielding colonists from cosmic radiation while orbiting the Sun like drifting space cities. It's bold, it's visionary, but it's not impossible. Just as our ancestors once crossed oceans to find new lands, we may soon cross the void of space to claim the stars, and the stepping stones on that journey are asteroids. As of now, only a handful of missions have touched them, but each mission returns with gifts from the ancient past and visions of a future where humanity thrives among the stars. So next time you look up and see a shooting star, remember, it might just be a piece of a lost world, or the first whisper of a future one. In the next episode of Infinity Beyond, we'll explore the weirdest and most terrifying asteroids ever discovered. Ones that spin at deadly speeds, hide in Earth's shadow, or are made almost entirely of precious metals. If you're loving this journey through space and time, hit that subscribe button and help us uncover the secrets of the universe, one cosmic stone at a time. In the vast silence of space, danger often comes in the most unassuming forms. A tiny object, barely a few hundred meters wide, spinning through the void, can carry the kinetic energy of 1,000 nuclear bombs. These are asteroids, but not just any asteroids. Today on Infinity Beyond, we're diving into the strangest, deadliest, and most fascinating asteroids ever discovered. Buckle up. Let's start with one that behaves like it's defying physics. 1999 KW4. This near-Earth asteroid is actually a binary system. Two rocks orbiting one another while they orbit the Sun. The larger of the two is about 1.3 kilometers wide, and its tiny companion, its moonlet, is about 500 meters across. But what's even more jaw-dropping is the shape of the main body. It's a perfect example of a spinning-top asteroid. Why? Because it's rotating so fast, once every 2.7 hours, that it bulges at the equator, creating a shape similar to a donut with a bulge around the waist. If it spun just a little faster, it could literally fling itself apart. Now imagine this object passing just 5 million kilometers from Earth. That's considered dangerously close in astronomical terms. Fortunately, NASA's Planetary Defense Program tracks these near-Earth objects, NEOs, closely. But KW4 is a chilling reminder that some asteroids don't follow the rules. And then there's Oumuamua. Technically classified as an interstellar object, Oumuamua streaked through our solar system in 2017. It came from another star system entirely and baffled astronomers with its cigar-like shape, unusual trajectory, and lack of a visible tail despite behaving like a comet. Some scientists suggested it could be a shard of a planet destroyed in another solar system. Others speculated it might be something else. An alien probe, perhaps? Harvard astronomer Avi Loeb famously didn't rule it out, arguing that its acceleration could not be explained by known physics alone. Whether it was natural or artificial, Oumuamua showed us that the cosmic neighborhood is far more mysterious than we ever imagined. Next up, 16 Psyche. The asteroid made of almost pure metal. This object, located in the asteroid belt, is so massive, over 220 kilometers in diameter, that NASA is planning a dedicated mission just to study it. What makes Psyche extraordinary is its composition. It's believed to be almost entirely made of iron and a nickel, similar to the core of a terrestrial planet. In fact, some scientists believe Psyche is the exposed core of a failed planet, a body that was stripped of its outer layers by violent collisions in the early solar system. If that's true, Psyche is our only opportunity to directly study a planetary core without having to drill through thousands of kilometers of rock. And get this, the estimated value of Psyche's metal content is $10 quintillion, more than the entire global economy. But don't worry, space mining isn't going to crash our markets anytime soon. If metallic monsters don't scare you, how about a tumbling twin? Meet 4179 Tutatis. This irregularly shaped asteroid rotates in a chaotic, non-principal axis manner. That's a fancy way of saying it tumbles through space like a drunk football. This bizarre motion is caused by gravitational interactions with Earth and other planets. In 2004, when Tutatis passed just 1.5 million kilometers from Earth, radar imaging showed it had two distinct lobes, making it resemble a peanut or a dumbbell. Tutatis is unpredictable. Its spin axis changes over time, which makes long-term orbit predictions more difficult. It's not an immediate threat, but it reminds us how unruly and unpredictable some of these objects can be. And then there are the fast rotators, like 2008 HJ. This tiny asteroid, just 12 meters wide, completes a full rotation every 42 seconds, the fastest spin rate of any natural object in our solar system. At that speed, the only thing holding it together is cohesive molecular forces, because gravity isn't strong enough. If it spun just a bit faster, it would disintegrate into a cloud of dust and pebbles. These superfast rotators challenge our understanding of material strength in space. What are they made of? How did they survive so long? The answers are still unfolding. Let's shift to another class of asteroids, Earth Trojans. These objects share Earth's orbit around the Sun, but remain hidden in gravitational sweet spots known as Lagrange points. One confirmed Earth Trojan is 2010 TK7, which orbits the Sun 60 degrees ahead of Earth in the same orbital path. Because of their positions, these objects are extremely hard to detect from Earth. Who knows how many more could be lurking, unseen, quietly trailing, or leading us on our annual voyage around the Sun. Of course, we can't forget the potentially hazardous asteroids, the ones that are large enough and close enough to pose a real danger to our planet. NASA and other agencies monitor thousands of these. One of the most closely watched, it is 90942 Apophis. Originally feared to have a high probability of striking Earth in 2029, updated calculations have since ruled that out. Still, it will pass within 31,000 kilometers of Earth's surface. That's closer than some satellites. On that day, you might be able to see it with the naked eye, streaking across the sky like a star that got too curious. Asteroids may be small, but they are cosmic powerhouses, each one unique, each one unpredictable. They carry secrets from the dawn of the solar system. Some are metallic cores, some are icy relics, some are interstellar visitors. And all of them remind us how fragile and dynamic our solar system really is. But beyond the fear, there's awe. These objects are not just threats, they are gateways to knowledge, testaments to time, and potential allies in our quest to explore the cosmos. In the next episode of Infinity Beyond, we'll look at the mythology and mystery behind asteroid names, from Roman goddesses to ancient warriors, and what these names reveal about humanity's relationship with the cosmos. If you haven't subscribed yet, now's the time. Join us as we continue our journey through the wild, weird, and wonderful world of asteroids and beyond. In our quest to map the heavens, humanity has discovered hundreds of thousands of asteroids, each one tumbling through space, ancient and enigmatic. But have you ever wondered how these cosmic rocks got their names? Why do we call them Ceres, Vesta, or Pallas? What do goddesses, heroes, and even fictional characters have to do with space science? Welcome back to Infinity Beyond. Today, we explore the fascinating intersection between mythology and astronomy, and how the names of asteroids reveal more about us than about the rocks themselves. When astronomers first began discovering asteroids in the early 1800s, they quickly ran into a challenge. What do you call these strange new worlds? Planets already had names rooted in Roman mythology: Mercury, Venus, Mars, Jupiter, and so on. So when Giuseppe Piazzi discovered the very first asteroid in 1801, he followed tradition and named it Ceres after the Roman goddess of agriculture. Ceres wasn't just a random choice. In mythology, Ceres was the protector of grain and fertility, deeply revered in Roman culture. Piazzi chose the name in honor of Sicily, where he lived, an island known for its fertile lands. Soon after, as more asteroids were found, the mythological trend continued. The second discovered asteroid was named Pallas, after Pallas Athena, the Greek goddess of wisdom and war. Then came Juno, queen of the gods, Vesta, goddess of the hearth, and Astrea, goddess of justice. Each of these early discoveries echoed the grandeur of ancient legends. These were not just floating rocks, they were celestial monuments named after powerful female deities. And for good reason. Astronomers at the time believed they might be discovering new planets. As the number of known asteroids grew, however, astronomers began to run out of major mythological names. So they expanded deeply. Asteroids began to be named after mythical heroes, like Achilles, Hector, and Odysseus. Then came muses, nymphs, and even spirits from Norse, Hindu, Egyptian, and Celtic traditions. One striking example is 433 Eros, named after the Greek god of love. When it was discovered in 1898, it was the first near-Earth asteroid ever found. Appropriately enough, Eros would come very close to Earth, an intimate cosmic dance, fitting for a god associated with desire and proximity. But not all names stayed in the realm of myth. As time passed, asteroid naming got a little weirder. In the 20th and 21st centuries, scientists were allowed more freedom in naming celestial bodies. Today, you'll find asteroids named after Mozart, Beethoven, and Bach, celebrating music; Albert Einstein and Marie Curie, honoring science; Mr. Spock, Luke Skywalker, and even James Bond. Yes, really. There's an asteroid named 2309 Mr. Spock, not directly after the Star Trek character, but after the discoverer's cat, who was named Spock after the character. The International Astronomical Union has since banned naming space objects after pets, but the name stuck. And in recent years, some asteroids have been named after social figures and cultural icons. For instance, there's 3028 Denzel for Denzel Washington, 274301 Wikipedia, and 51985 Kirby, named after the famous video game character. But how does the naming process work? Once an asteroid is discovered and its orbit is well defined, it receives a provisional designation, something like 2025 AB4. Once confirmed, the discoverer gets the honor of suggesting a name. However, the final approval lies with the International Astronomical Union, IAU. Their guidelines are surprisingly specific. For example, names should be 16 characters or fewer. They shouldn't be offensive or too similar to existing names. Political or military figures must be dead for at least 100 years, unless they're culturally significant beyond politics. This system creates a unique cultural mirror. Every asteroid named tells us something about what we value at that point in history. In a way, the asteroid belt is a skybound library of humanity's icons, from ancient goddesses to modern artists. Let's go back to 16 Psyche, the metallic asteroid we explored earlier. Named after the Greek goddess of the soul, Psyche represents human emotion, inner strength, and transformation. A fitting name for a body that could reveal the deepest layers of planetary cores. Then there's 19955 Bennu, the target of NASA's OSIRIS-REx mission. This asteroid was named by a 9-year-old boy in a NASA contest. He chose the name after the Egyptian deity Bennu, a bird associated with rebirth and creation. The choice was symbolic. The spacecraft, like the Bennu bird, was collecting material to bring life-giving knowledge back to Earth. It's poetic, isn't it? In many ways, naming asteroids is our way of taming the unknown. It's an ancient instinct. By naming something, we give it identity, meaning, and a place in our story. Through these names, we also create a bridge between science and storytelling. Because for all our advanced technology, we are still humans, still drawn to myth, still seeking patterns in the stars. Astronomy, after all, is not just about data. It's about wonder. It's about standing under the night sky and whispering stories about gods and monsters, music and love, heroes and history. And in the asteroid belt, scattered across millions of kilometers, those stories live on, written in the language of orbits and light. So the next time you hear the name of an asteroid, take a moment. Ask yourself, why that name? What does it mean? You might find a myth you've never heard, or a connection to someone who changed the world. Because up there, drifting in eternal silence, are pieces of our past and reflections of our culture, orbiting the sun like silent storytellers. In the next episode of Infinity Beyond, we'll take a sharp turn from mythology to menace as we explore how astronomers track dangerous asteroids and what planetary defense systems we're building to protect Earth from a potential impact. Don't miss it, and don't forget to subscribe and join us as we continue this voyage through the asteroid belt and into the mysteries beyond. Imagine looking up at the night sky and seeing a fiery streak racing toward Earth. Not a shooting star, not a meteor shower, but an asteroid, massive, unstoppable, on a collision course with our planet. It sounds like science fiction, but it's not. Throughout Earth's long history, asteroids have struck our planet again and again, with devastating consequences. The most famous? The Chicxulub impact, 66 million years ago. A 10-kilometer-wide asteroid slammed into what is now the Yucatan Peninsula in Mexico, triggering a chain reaction that wiped out the dinosaurs and nearly 75% of all life on Earth. That wasn't a close call. That was a reset button. So the question is, what if it happens again? And more importantly, can we stop it? Welcome to Infinity Beyond, where today we explore the cutting-edge science of planetary defense, Earth's line of protection against cosmic impacts. Let's start with the basics. Every year, Earth is bombarded with more than 100 tons of space material, mostly harmless dust and pebbles that burn up in the atmosphere. But once in a while, something bigger sneaks through. In 2013, a 20-meter-wide meteor exploded over Chelyabinsk, Russia. It released 30 times more energy than the Hiroshima bomb, shattered windows in 6 cities, and injured over 1,500 people. And that was a relatively small object. Now imagine an asteroid hundreds of meters across, or a kilometer, or more. To face that kind of threat, we need more than hope. We need a plan. The first step in planetary defense is detection. NASA's Near-Earth Object Observations Program, also known as SpaceGuard, tracks thousands of asteroids and comets that come close to Earth's orbit. These objects are called Near-Earth Objects, or NEOs. NEOs are classified based on size and proximity. The ones we worry about most are potentially hazardous asteroids, PHAs, those larger than 140 meters and that pass within 7.5 million kilometers of Earth. To find them, astronomers use optical telescopes, radar imaging, and soon, a new generation of space-based infrared observatories like NEO Surveyor, set to launch in the coming years. But detection isn't enough. Once we find a threat, we need a way to deflect it. And that brings us to one of the most ambitious experiments in planetary defense history, DART. In 2022, NASA's Double Asteroid Redirection Test, DART, became the first mission ever to intentionally crash a spacecraft into an asteroid to change its trajectory. Target, Dimorphos, a 160-meter-wide moonlet orbiting a larger asteroid, Didymos. Goal? Hit it hard enough to slightly alter its orbit, a proof of concept that we can deflect an asteroid without blowing it up. The result? A stunning success. DART struck Dimorphos at 6.6 kilometers per second. Observations from Earth showed that its orbit changed by more than 30 minutes, far exceeding expectations. This wasn't just a test, it was a turning point. It showed that kinetic impactors, spacecraft designed to slam into asteroids, are a viable method of planetary defense. But that's only one method in our planetary defense toolbox. Let's explore a few more ideas scientists are actively researching. Gravity tractors. A spacecraft could fly alongside an asteroid for months or even years, using gravitational attraction to subtly pull the asteroid off course. It's a slow process, but very precise. Ion beam shepherds. By directing a continuous stream of ions at an asteroid, a spacecraft could gradually push it at using the force of particle momentum. Think of it as space-level pressure washing. Solar sails and paint. Yes, even painting an asteroid could help. By altering its albedo, reflectivity, we can change how it absorbs sunlight, thereby tweaking its path via the Yarkovsky effect, a real force caused by thermal radiation. Nuclear explosions. Considered a last resort, detonating a nuclear device near an asteroid surface could either vaporize part of it or nudge it off course. Unlike in Hollywood movies, the goal isn't to blow the asteroid to bits, but to create a controlled force that alters its trajectory. Each method has pros and cons. Timing is critical. The earlier we detect a threat, the less force we need to deflect it. But what if we don't catch it in time? That's where emergency response plans come in. Space agencies and governments run regular simulations, called planetary defense drills, where they model what would happen if an asteroid were heading toward Earth with just months to spare. In these scenarios, they consider evacuation plans for impact zones, strategies to protect infrastructure, communication protocols to prevent mass panic. One such simulation in 2021, coordinated by NASA and ESA, imagined a fictional asteroid on track to strike Europe. The outcome? We couldn't stop it in time. The message was clear: early detection is everything. So, how prepared are we, really? As of now, astronomers have cataloged over 90% of NEOs larger than 1 kilometer. But for objects between 100 to 500 meters wide, the ones still capable of regional devastation, we found only about 40%. That's why the next generation of sky-scanning telescopes is so critical. One of the most anticipated projects is the Vera C. Rubin Observatory in Chile. Once operational, it will scan the entire sky every 3 nights, dramatically increasing our ability to detect smaller, faster, and more elusive space rocks. We're in a race against time, not because an asteroid is headed for us now, but because we know one day one will be. It's not a question of if, it's a question of when. But here's the good news. We're no longer passive observers of fate. For the first time in human history, we have the technology, the knowledge, and the will to defend our world. Think about that. A species that once feared the sky now sends machines into space to protect the planet. We've gone from gazing at stars in wonder to pushing back against cosmic threats. And that's just the beginning. In the next episode of Infinity Beyond, we shift our focus to a deeper question. What if we find evidence that an asteroid impact created life instead of destroying it? Could the seeds of life have arrived on a meteorite? And if so, what does that mean for our origin story? Subscribe now and join us as we explore the fine line between destruction and creation, between extinction and evolution. The universe may be dangerous, but it's also full of wonder. What if the very thing we fear, the impact of an asteroid, was actually the spark of life? It's a wild idea, but one that scientists around the world are taking more and more seriously. Could it be that the origins of life on Earth weren't found in volcanoes or ancient oceans, but instead in the icy heart of a distant asteroid? Welcome back to Infinity Beyond, where today we journey into one of the most profound and controversial questions in science. Did life on Earth begin with a rock from space? Let's rewind time. Not just thousands or millions of years, but billions. Roughly 4.5 billion years ago, Earth was a molten hellscape, a violent, unstable planet constantly bombarded by meteors, comets, and asteroids. This period, known as the Late Heavy Bombardment, lasted hundreds of millions of years and reshaped the surface of the Earth many times over. But in that chaos, something miraculous might have happened. As asteroids slammed into our young planet, they didn't just bring destruction, they brought ingredients. In 1969, a meteorite crashed near Murchison, Australia. When scientists examined it, they were shocked to find something extraordinary: amino acids, the fundamental building blocks of proteins and, by extension, life. Since then, researchers have discovered over 70 amino acids in the Murchison meteorite. including several that do not occur naturally on Earth. Even more astonishing, some of them showed a preference for left-handedness, a property known as chirality, which is crucial for the structure of living cells. This discovery sparked a radical theory, panspermia. Panspermia proposes that life, or at least its building blocks, originated not on Earth, but elsewhere in the universe, and were delivered to our planet via meteors, comets, or asteroid fragments. And it's not as far-fetched as it once seemed. In fact, laboratory simulations have shown that amino acids can form in space. Combine that with water-bearing asteroids and icy comets, and you have a perfect delivery system, sending prebiotic chemistry straight to Earth. But it gets even more intriguing. Recent analysis of the Ryugu and Bennu samples, brought back by Hayabusa 2 and OSIRIS-REx, confirmed the presence of organic molecules and hydrated minerals. These are materials that formed in the presence of water, long before Earth cooled down enough to support liquid oceans. Imagine this, before Earth had lakes, rivers, or seas. Asteroids were already carrying ice and carbon-based molecules through the solar system, crashing down onto the surface, seeding the planet with the first whispers of life. These weren't just dead rocks, they were cosmic care packages, sent from the stars. So if life didn't originate on Earth, where did it come from? That's the million-dollar question. Some scientists believe the essential ingredients were created in interstellar dust clouds, long before the solar system even formed. These molecules, trapped in icy grains, eventually coalesced into asteroids and comets that became part of our planetary neighborhood. Others take it even further. They propose that microbial life itself might have existed on other planets, like Mars, and was blasted into space by impacts, eventually landing on Earth and surviving the journey. Incredibly, studies have shown that certain bacteria can survive the vacuum of space, extreme radiation, and temperature fluctuations. In 2020, a strain of Deinococcus bacteria was exposed to space for 3 years on the outside of the ISS and survived. So the notion that life could travel across space isn't just speculation, it's experimentally plausible. This changes everything. If life on Earth started with an asteroid, then life elsewhere might be far more common than we ever imagined. It means that every star system with a rocky planet and a few asteroid belts might have its own story of life. Maybe not advanced civilizations, but at the very least, microbial life, riding along on space rocks, waiting to crash into a fertile world. And if panspermia is real, Earth might not be unique. We might be part of a galactic web of life, connected not by communication or technology, but by fragments of rock and ancient molecules drifting between stars. Think about it. You're made of carbon, hydrogen, nitrogen, elements forged in the hearts of stars. But the arrangement of those atoms, the patterns that give rise to cells and consciousness, may have come from somewhere far beyond. You are, quite literally, the child of a cosmic collision. But as we reach for answers, we must also ask, how do we prove it? That's where missions like Mars Sample Return, Europa Clipper, and future asteroid explorers come into play. If we find similar amino acids or organic compounds on Mars, Europa, Enceladus, or even in the subsurface oceans of distant asteroids, it will suggest a shared cosmic ancestry. And that, more than anything, would prove we are not isolated miracles, but part of something much bigger. There's a beautiful irony in all of this. The same forces that have threatened life, asteroid impacts, cosmic radiation, meteor storms, may have also created it. Destruction and creation, chaos and order, extinction and evolution. They are not opposites. They are partners, dancing together across cosmic time. An asteroid killed the dinosaurs. Another may have brought the spark of life. And in a distant future, we may ride aboard asteroids ourselves, using them as shelters, transports, or even launching pads into the deep unknown. In the next episode of Infinity Beyond, we explore one of the most haunting questions of all. What if a massive asteroid is already on its way, and we just haven't seen it yet? Are we truly prepared? Or is a ticking clock already counting down? Make sure to subscribe, share, and stay curious, because the universe is full of secrets, and some of them might just be buried inside a rock. We gaze up at the stars with wonder. We map the skies, study exoplanets, and celebrate space exploration. But what if, in all our curiosity, we're missing something? What if, hidden among the millions of rocks hurtling through the void, there's one heading straight for us? No one sees it yet. No alerts, no sirens, just silence. Until it's too late. Welcome back to Infinity Beyond, and in this chilling episode, we ask the question no one wants to hear out loud. What if a planet-killer asteroid is already on its way, and we don't know it yet? Let's begin with a sobering truth. We don't see everything. As advanced as our telescopes are, as fast as our computers have become, there are still blind spots, huge areas of the sky we simply can't observe effectively, especially during daylight hours or from certain latitudes. Asteroids that approach from the direction of the sun are particularly dangerous. They remain invisible until they're far too close. In 2013, the Chelyabinsk meteor exploded over Russia with the force of 500,000 tons of TNT. It was never detected before impact. Why? Because it approached from the sunward side, completely hidden by solar glare. Now imagine something 10 times larger, approaching from the same blind spot. You wouldn't see it. You wouldn't know. This is not just a thought experiment, it's a real threat. In 2022, a newly discovered asteroid, 2022 EB5, was detected just 2 hours before impact. Fortunately, it was small and exploded harmlessly over the Arctic Ocean. But the clock was real. 2 hours. Now imagine that timer reading 2 days. Or 2 weeks. How would the world respond? Would governments prepare? Would people panic? Would we even believe the news in time? NASA, ESA, and space agencies around the globe are working tirelessly to detect these objects. Missions like NEO Surveyor and telescopes like the upcoming Vera Rubin Observatory will vastly improve our sky coverage. But even with all these advances, our detection rate is far from perfect. Out of the estimated 25,000 near-Earth asteroids larger than 140 meters, we've only found just over 10,000. That leaves more than half unaccounted for. And we're not even talking about the smaller ones yet, like the 50-meter-wide object that hit Tunguska, Siberia in 1908, leveling 2,000 square kilometers of forest. That one came out of nowhere too. So, let's play out the scenario. Imagine astronomers detect a large asteroid, say 400 meters wide, on a confirmed collision course with Earth. Impact in 30 days. What happens next? Step 1. Verification. Dozens of observatories worldwide would rush to confirm the data. Once confirmed, the information would be passed to planetary defense agencies, and then to world leaders. Step 2. Global coordination. The United Nations, NASA, ESA, and national governments would likely convene emergency sessions. The media would pick it up. Social networks would go into overdrive. Misinformation would spread as fast as panic. Step 3. Impact prediction. Scientists would determine where it will strike, when, and what the blast radius would be. If it's over the ocean, expect tsunamis. Over city-leveling destruction. Atmospheric entry would cause fireballs, shockwaves, even nuclear winter if the asteroid is large enough. Now here's the twist. We might not be able to stop it. Unless we had years of warning and a spacecraft ready to launch immediately, there's not much we could do to deflect it in just 30 days. So the response becomes about mitigation, evacuations, impact zone preparation, civil defense drills. But let's be honest, No country is ready for a truly global asteroid event. But here's where hope returns. The more we invest now in early detection, the better chance we have to prevent panic and save lives. Tools like DART-style missions, kinetic impactors, nuclear deflection experiments, and automated space telescopes that scan the sky every night. These are the foundations of a future where no impact ever catches us off guard again. And perhaps, one day, our descendants will look back and say, they were the generation that learned how to protect the Earth from space. There's also another possibility, one far less terrifying, but just as humbling. What if the asteroid is real, but it misses? Not by much, maybe by 10,000 kilometers, just enough to light up the sky and remind us how fragile we truly are. We breathe a sigh of relief. The news calms. Life returns to normal. Until next time. Because space doesn't care about our calendars or our comfort. It just keeps moving. And so do the rocks. So what can you do? You can stay informed. You can support science. You can help share the message that planetary defense is not science fiction. It's a real responsibility. And you can look up, not with fear, but with curiosity and awe. Because, as dangerous as the cosmos can be, it's also full of beauty, mystery, and meaning. And we are lucky to be here, to witness it, to study it, and to protect what we've built. In the next episode of Infinity Beyond, we flip the story completely. What if we don't wait for asteroids to come to us? What if we go to them, not just to study or mine them, but to live on them? Asteroids as future homes, research stations, or even interstellar ships. Sounds crazy? Maybe not. Subscribe now and join us on the next leg of our journey, because the future is no longer science fiction. It's just waiting to be written. We've talked about asteroids as threats. We've explored how they may have seeded life or ended it. But what if, instead of fearing them, we embraced them? What if asteroids became more than debris? What if they became destinations? Homes, stations, refuges, gateways to the stars. Welcome back to Infinity Beyond. In this episode, we ask a bold question. Could we live on asteroids? Not just visit them, but transform them into the next frontier of human civilization. Let's be clear. This isn't just science fiction anymore. It's a concept backed by serious space agencies, engineers, and even private companies. Why? Because asteroids offer something that few other places in the solar system can match: abundant resources, low gravity, strategic positioning, and in some cases, natural protection from radiation. The vision is simple. If we can land on them, we can mine them. If we can mine them, we can build on them. And if we can build, we can live. Let's start with why. Asteroids are rich in everything we need for off-world life. Some contain water ice, essential for drinking, growing food, and breaking down into oxygen and hydrogen for breathable air and rocket fuel. Others contain precious metals like platinum, cobalt, and nickel. Materials that could support space-based construction or be returned to Earth. And then there are carbonaceous asteroids, loaded with organic compounds. In short, they're not just space rocks. They're self-contained supply depots floating in space. So why build on Earth and launch it into orbit, when the raw material is already up there, waiting? Now, let's talk about how. Living on an asteroid presents unique challenges, but none that are unsolvable. First, the gravity. Asteroids are small, meaning their gravity is weak. A human could jump and launch into space. That's a problem for walking, for building, and for keeping people healthy. Solution? We anchor habitats inside the asteroid. Think of a rotating habitat built within the hollowed-out interior of a large asteroid, like 16 Psyche or Eros. By spinning the structure, we can simulate artificial gravity using centrifugal force. Second, radiation. Unlike Earth, asteroids have no atmosphere to protect from cosmic rays, or solar radiation. But this is where the asteroid helps us. By tunneling into the rock, living inside, not on top, we gain natural shielding. A few meters of dense material can block most harmful radiation, making underground asteroid habitats safer than those on the surface of the Moon or Mars. Third, the environment. No air, extreme temperatures, micrometeoroids. The solution? Pressurized modules, thermal regulation, and regenerative life support systems, the same technology being developed for long-term Moon and Mars missions. In short, yes, it's hard, but no, it's not impossible. Now let's dream bigger. Asteroids could become more than just homes. They could be transport vessels. That's right, mobile space stations. Picture this. Take a medium-sized asteroid, hollow it out, install life support systems, propulsion units, and radiation shielding. What you have now is an interstellar arc capable of slow but sustainable travel through the solar system and beyond. These generation ships could carry settlers, researchers, or even entire biomes. Using ion propulsion or solar sails, they might cruise between planets, refueling at other asteroids along the way. In time, they could be the key to interstellar migration, humanity's lifeboats drifting toward new worlds. But why start with asteroids? Because they're everywhere. There are over 1.1 million known asteroids in our solar system, ranging from meter-wide pebbles to dwarf planet-sized giants. Some orbit near Earth. Others live in the main asteroid belt between Mars and Jupiter, and some even orbit closer to the Sun or beyond Neptune. These space rocks are like stepping stones across the void, a network of habitats, refueling stations, or research outposts scattered across the cosmos. Asteroids offer something that planets don't: low escape velocity. It's far easier and cheaper to launch a spacecraft from an asteroid than from a planet with strong gravity. They're the perfect base camps for deeper exploration. Private companies are already betting on this future. Firms like Planetary Resources, Deep Space Industries, and Asteroid Mining Corporation have proposed missions to scout and eventually mine near-Earth asteroids. While progress has been slow, the vision remains: a self-sustaining space economy, fueled by off-world resources. Meanwhile, NASA's upcoming Psyche mission, scheduled to launch soon, will study a metallic asteroid in unprecedented detail. The findings could guide future efforts to mine, build, or settle on similar bodies. But perhaps the most exciting thing is what this all means for the human story. For most of history, we've lived in fear of asteroids, as omens, as destroyers. But now, we stand at the edge of a new relationship, one where they are no longer agents of extinction, but allies in expansion. We no longer run from the rocks. We reach for them. And one day, we may live among them, not as survivors, but as pioneers. In the next episode of Infinity Beyond, we dive into something even stranger. What if there are alien artifacts on asteroids? Could intelligent life have passed through our solar system and left behind a clue on a rock, quietly orbiting, just waiting to be found? Don't miss it. Subscribe now. Because the universe is full of questions, and together we're going to chase the answers. We've studied asteroids as threats, as origins of life, as future homes for humanity. But what if there's something more? What if some asteroids aren't just ancient space rocks, but vaults of secrets, artifacts, relics, leftovers from civilizations not our own? Welcome back to Infinity Beyond, and in this mind-bending episode, we dare to ask, could there be alien technology hidden on asteroids, and have we simply failed to notice it? Let's begin with what sounds like science fiction, but is actually serious science. In 2017, renowned Harvard astrophysicist Dr. Avi Loeb made headlines when he proposed that an interstellar object named Oumuamua might be more than it seemed. It had entered our solar system from another star. It was moving too fast to be from here. It had an unusual, elongated shape, like a pancake or cigar, and, strangely, it accelerated without a visible tail, unlike any known comet. Loeb's radical suggestion? Oumuamua might be an alien probe, a relic of a distant civilization. Not a functioning spacecraft, perhaps, but maybe a derelict scout, drifting silently, its purpose lost to time. His theory was, and still is, controversial, but it opened the door to a possibility. If alien civilizations explored space millions or even billions of years before us, where are their leftovers? Enter the asteroid belt. The region between Mars and Jupiter is home to millions of rocks, many untouched since the formation of the solar system. It's stable, cold, quiet, a perfect storage space for something you want to hide or preserve. Let's say an advanced civilization once passed through our solar system. Maybe they sent probes, monitoring devices, or seeding mechanisms. Where would they store them? On planets? Risky. Volcanism, erosion, atmosphere? On the moon? Visible, exposed to radiation, dust storms. But on a lonely asteroid, spinning in silence for eons? Perfect. Here's where things get weird. In the best way. In 2011, scientists using the Allen Telescope Array pointed their antennas at near-Earth asteroid 99 RQ-36, now known as Bennu, to listen. They weren't just scanning for composition or orbit. They were checking for radio signals. Why Bennu? Because it's old, primitive, and has anomalous characteristics, including a high ratio of hydrated minerals and surface features difficult to explain through known geological processes. No signals were detected, but the fact that scientists tried tells us something important. This is not just science fiction. It's a legitimate question in the search for extraterrestrial intelligence. If aliens visited the solar system, would they leave behind evidence? And if so, where? Here's another example. Asteroid 433 Eros was visited by NASA's Near-Shoemaker spacecraft in 2000. It took detailed photos of the surface, and some images showed rectilinear features, straight edges, sharp shadows, grid-like cracks. Most scientists attributed this to natural geological activity and stress fractures. But some observers wondered, are these signs of artificiality? The same has been asked of asteroid Phobos, one of Mars' moons, which some argue is a captured asteroid. Its monolith-like object, a massive upright block casting a long shadow, has been called by some a Martian obelisk. Buzz Aldrin himself once said, "We should visit the moon of Mars. There's a monolith there. When people find out about it, they will say, 'Who put that there? Who put that there?'" Of course, we must approach this topic with skepticism and scientific rigor. Extraordinary claims require extraordinary evidence. But the exciting part? We're finally in a position to start looking. Missions like OSIRIS-REx, Hayabusa 2, and the upcoming Psyche mission are giving us our first up-close looks at these ancient bodies. And who knows what we'll find when we start digging deeper. Literally. Imagine this. A future crew lands on a carbon-rich asteroid. While excavating for water, ice, or metal, their drill hits something unexpected. A geometric shape. Hollow, metallic, resonant. Inside, data, blueprints, signals. A time capsule not from Earth, but from elsewhere. Yes, it sounds like a sci-fi movie, but so did spaceflight 100 years ago. So did landing on the moon. There's even a term for this search, archaeology of the cosmos. It's a field that doesn't look for active civilizations, but fossil evidence of intelligence. Satellites, probes, beacons, dead tech, in places no one ever expected. Some scientists now include asteroids as targets in SETI searches, not for radio transmissions, but for infrared signatures, thermal anomalies, or non-natural mineral compositions. Because if we only look for living aliens, we might miss the signs of those long gone. And here's a final thought. What if we are the relics? What if long ago, life was seeded across solar systems by asteroid-borne panspermia, as discussed in our last segment? Then in that sense, you and I, our DNA, our intelligence, are the echoes of something ancient, planted like seeds, now flowering on Earth. Maybe there is no probe, no monolith. Maybe we are the evidence. In the next episode of Infinity Beyond, we return to more solid ground, literally. We'll explore how asteroid mining could launch a new space economy and why the first trillionaires might not be tech CEOs, but asteroid tycoons. Don't miss it. Subscribe. Because if the past is frozen in stone, the future might be carved from it. In the 19th century, gold rushes changed the course of nations. In the 20th, oil reshaped the global economy. But in the 21st, or perhaps the 22nd, the greatest resource race of all may happen in space. Welcome back to Infinity Beyond. In this episode, we explore a future that's rapidly moving from fiction to fact, asteroid mining, and how it could create the first trillionaire, revolutionize global industries, and transform our relationship with the solar system. Let's start with the big idea. Asteroids are more than floating rocks. They are treasure chests orbiting the sun, filled with water, metals, and rare elements. Some are composed of nickel and iron, just like Earth's core. Others contain platinum group metals, which are essential for electronics, green energy, and high-tech manufacturing. In fact, a single small asteroid, just a few hundred meters wide, could hold more platinum than has ever been mined in human history. The monetary value? Trillions of dollars. But the real value of asteroid mining isn't just about making someone rich. It's about unlocking a new economy. Imagine this. No more scarring Earth with deep mining pits. No more dangerous extraction from politically unstable regions. Instead, we look up and harvest resources off-world. Asteroid mining could enable off-Earth construction, space-based solar energy systems, propellant production for long-distance missions, and eventually, self-sustaining space habitats. It's not just about bringing material back to Earth. It's about fueling the future of space itself. So how does it work? There are three primary types of asteroids targeted for mining. C-type, carbonaceous, contain water, carbon-based molecules, and volatile compounds. Ideal for extracting water for life support or fuel, split into hydrogen and oxygen. S-type, silicaceous, rich in nickel, iron, magnesium. Good for structural materials and industrial use. M-type, metallic, composed mostly of metallic iron, cobalt, and platinum group elements. These are the real jackpots for precious materials. The process typically follows these phases. Prospecting. Identify a target asteroid using telescopes and spectral analysis. Exploration. Send robotic probes to analyze surface composition, gravity, and structure. Extraction. Mine the surface or interior using drilling, laser melting, or even microwave heating. Processing. Refine materials in space or return them to Earth for use. Sounds futuristic? Maybe. But the first steps have already begun. Companies like Planetary Resources, Deep Space Industries, and Asteroid Mining Corporation have been seriously researching asteroid mining for over a decade. While none have yet succeeded in full-scale operations, the technology is catching up. NASA's OSIRIS-REx proved we can land on and sample asteroids. Japan's Hayabusa 2 demonstrated surface impact and sample return. SpaceX and Blue Origin are building the rockets that might carry equipment to these distant targets. Meanwhile, the European Space Agency, ESA, and NASA are investing in situ resource utilization, ISRU. The idea of using materials already present in space to build, fuel, and sustain missions. In other words, why bring everything from Earth when space has what we need? Let's talk numbers for a moment. Asteroid 16, Psyche, a metallic giant over 200 kilometers wide, is estimated to contain $10 quintillion worth of metals. That's more than the entire global economy. Of course, if we brought that much metal back to Earth, it would crash the markets. But that's not the point. The real opportunity is in creating a self-sustaining ecosystem in space, where resources are mined, refined, and used off-world without burdening Earth's environment. There are also legal and ethical challenges. Who owns an asteroid? Can private companies claim territory in space? The Outer Space Treaty of 1967 says no nation can claim celestial bodies, but it's vague about private enterprise. More recent legislation, like the U.S. Commercial Space Launch Competitiveness Act and Luxembourg's space mining laws, give companies the right to own what they extract, though not the asteroid itself. Still, this legal gray area could lead to space disputes, economic imbalance, or even conflict if not addressed proactively. That's why many experts are calling for a new international framework, a Space Resources Accord, to ensure responsible, peaceful development. But make no mistake, the first country or company that successfully mines an asteroid will change history. They will have access to materials that could build space elevators, power orbital factories, or launch interplanetary missions at a fraction of current costs. And they may become the world's first trillionaire. But more importantly, they will help humanity take its next evolutionary step, becoming a spacefaring civilization that doesn't just explore the cosmos, but thrives in it. Let's pause for a second and let that sink in. You're living in the generation that may witness the first asteroid mine, the first space-based refinery, the first blueprint for an interplanetary economy. One day, our descendants may ask, where did the space age truly begin? And the answer might not be Apollo or Mars. It might be a nameless rock, drifting silently through space until someone saw not just a threat, but a future. In the next episode of Infinity Beyond, we bring it full circle. We revisit Earth and ask a pressing question. What happens when an asteroid actually does hit? From ancient impacts to modern simulations, we explore the science of impact events and what Earth's cratered history reveals about its future. If you've enjoyed this journey into the heart of asteroid mining, like, subscribe, and hit the bell, because the universe isn't waiting, and neither should we. They leave no warning, no time to prepare, just a flash of light, and a moment that changes everything. Welcome back to Infinity Beyond. In today's episode, we come home, to Earth, to uncover the ancient scars left behind by cosmic collisions, and ask the haunting question, what happens when an asteroid hits? Let's start with a truth that's often overlooked. Earth has been hit, many times. Our planet is a survivor in a solar system full of chaos, and though erosion, plate tectonics, and vegetation have hidden most evidence, scientists have uncovered more than 190 confirmed impact craters across the globe. Each one tells a story, some of destruction, some of extinction, and some of transformation. Perhaps the most infamous is the Chicxulub crater, buried beneath the Yucatan Peninsula in Mexico. 66 million years ago, a 10-kilometer-wide asteroid slammed into Earth at over 72,000 kilometers per hour. The impact released energy equivalent to 10 billion Hiroshima bombs. Firestorms swept across continents. Mega tsunamis swallowed coastlines. A thick cloud of dust and sulfur blanketed the sky, plunging the planet into darkness for months, possibly years. Photosynthesis collapsed. Ecosystems unraveled. Dinosaurs, once rulers of Earth, vanished. But from that destruction came a new era. Mammals rose. Eventually, humans appeared. That impact didn't just end a chapter, it opened a new one. But Chicxulub is only one crater among many. In Russia, the Popogi crater spans 100 kilometers. In Canada, the Manicouagan crater, visible from space, was caused by an impact 214 million years ago. And then there's the Vredefort Dome in South Africa, an ancient wound more than 300 kilometers wide, formed over 2 billion years ago. These aren't relics of the past, they're warnings written in stone. The most sobering part? It doesn't take a dinosaur killer to cause devastation. In 1908, over a remote forest in Tunguska, Siberia, a 50-meter object exploded mid-air. The resulting shockwave flattened 2,000 square kilometers of forest, an area the size of a major city. If that explosion had happened just a few hours later, over London, Tokyo, or New York, the death toll would have been in the millions. And remember the Chelyabinsk event in 2013? That was just 20 meters wide, and still injured 1,500 people with shattered glass and a massive atmospheric blast. These aren't ancient events, they're reminders that space is still watching. So, what would happen if a similar impact occurred today? Let's imagine a 300-meter-wide asteroid, large enough to wipe out a major metropolitan region, is discovered. Impact in 72 hours. What do? There's no time to launch a deflection mission, no time for global politics, only time to calculate the impact zone and evacuate. But that's just the start. The air blast could level buildings for hundreds of kilometers. Shock waves would circle the globe. And if it struck an ocean, mega tsunamis would devastate coastlines. Even worse, if the asteroid is over 1 kilometer wide, it could trigger global climate collapse, a modern-day nuclear winter. Billions could be at risk. But here's the twist. We might not even know it's coming. As discussed in Segment 9, many near-Earth objects remain undetected, especially smaller ones. The sky is vast, and asteroids are dark, fast-moving, and silent. That's why early detection is our first and most important defense. It's also why missions like NEO Surveyor and telescopes like Vera Rubin Observatory are critical. They give us the lead time we need. And yet, not all impacts are bad. Ironically, they've shaped Earth in remarkable ways. Some scientists believe asteroid impacts delivered water to our planet billions of years ago. Others may have carried the amino acids and organics that kick-started life. Even mass extinctions cleared ecological space for new species to thrive. So while impacts can destroy, they also create. They are not just catastrophes. They are cosmic resets. Today, we stand at a turning point. For the first time, humans have the tools to see these threats coming and possibly stop them. We've moved from superstition to simulation, from helplessness to strategy. We know what to look for. We know how to respond. And with every mission, every telescope, every line of code, we grow better prepared. But vigilance must be constant, because space doesn't give warnings, only moments. In the next episode of Infinity Beyond, we'll take a hopeful leap forward. If we one day colonize the asteroid belt, what would life look like there? Could we build cities within asteroids, powered by solar energy, populated by explorers, scientists, even families? Tune in as we imagine the architecture, culture, and survival of asteroid civilizations. Until then, like, subscribe, and stay curious, because every crater is a story, and the next one might be ours to write. We once lived in caves, then in cities. Now we reach for the stars. But what if the next leap in human civilization isn't on Mars or the Moon, but inside the cold, hollow heart of a spinning rock? Welcome back to Infinity Beyond. In this episode, we journey into the realm of future architecture, social engineering, and cosmic ambition. We ask the bold question: what would it take to build an actual city on an asteroid? Let's start with location. Not all asteroids are created equal. To host human life, we'd need a stable, low-radiation, and relatively large asteroid. Candidates include Ceres, a dwarf planet in the asteroid belt, with water ice and possible subsurface oceans. 16. Psyche, a metallic giant, perfect for construction and material sourcing. Eros or Didymos, near-Earth asteroids with proximity advantages. These bodies are rich in resources, naturally protected from extreme solar radiation, and situated perfectly as launch hubs for interplanetary travel. But how do you turn a lifeless rock into a living world? Step 1. Go underground. Living on the surface of an asteroid would expose settlers to solar radiation, micrometeorites, temperature swings of hundreds of degrees. The solution? Tunneling inside. Asteroid interiors offer natural protection. Engineers envision habitats carved into the core, insulated from space, pressurized with breathable air, and lit by artificial sunlight. Walls made of regolith could block radiation. Rotating modules could simulate gravity. Modular systems would allow cities to grow like coral, organically, piece by piece. In a way, we'd be creating underground starships embedded in rock. Step 2. Energy and life support. Solar energy would be the obvious choice, particularly for asteroids closer to the Sun. Large mirrors on the surface could reflect sunlight into light tunnels, feeding indoor farms and energy grids. Water extracted from ice deposits would be filtered for drinking, split for oxygen and hydrogen fuel, and used in closed-loop recycling systems. Carbon would come from regolith, oxygen from electrolysis. Waste from humans and plants would become fertilizer. This would be a self-contained ecosystem, a miniature Earth, an asteroid biosphere. Step 3. Society. Once the infrastructure is stable, a new question arises. What kind of culture would grow in an asteroid city? Would we carry Earth's traditions, cities, nations, borders? Or would new societies emerge, adapted to their isolated high-tech environments? Life inside an asteroid would demand collaboration. Every breath would rely on machines. Every mistake could be fatal. Social structures might favor technocratic governance, collective decision-making, rotational leadership among engineers, biologists, navigators. Laws would evolve. So would identity. Imagine children born on Psyche or Ceres who've never seen an open sky. What would they call home? Now imagine dozens, hundreds of such cities. A chain of asteroid colonies forming a civilizational web across the solar system. Each city could specialize. One might be a research outpost, studying alien microbes trapped in ice. Another, a manufacturing hub, refining metals for use in orbital construction. Another, a spiritual sanctuary, home to philosophers and artists contemplating the silence between stars. Trade would flow between them. Ideas would bounce across light minutes. And slowly, humanity would evolve into a multi-world species, not confined to a single blue marble. Of course, the challenges would be immense. Psychological strain from isolation, dependence on machinery, risk of decompression or habitat breach, moral dilemmas about reproduction, governance, and resource control. But so too were the challenges of the first seafarers, explorers, and pioneers on Earth. They faced stump-seed, disease, starvation, and still they sailed. Because that's what we do. We push forward. We settle the unknown. Asteroid cities may begin as scientific outposts, then mining colonies, then modular habitats. But in time, they may become cradles of new cultures, the seedbeds of post-Earth humanity. They may be where the first asteroid-born citizen takes their first breath, the first interstellar mission launches, or the first declaration of independence beyond Earth is written. They may be where we become something more, not just Earthlings, but Solarians, Astro-citizens, children of the belt. In the next episode of Infinity Beyond, we ask one of the biggest questions in planetary science. Could there be a Planet 9, a massive, undiscovered world lurking beyond Neptune, shaping the orbits of distant objects and rewriting everything we know about our solar system? It's a mystery that's baffled astronomers for decades, and we're diving into the evidence, the theories, and what happens if we find it. So don't forget to like, subscribe, and ring the bell, because the universe is vast, and your seat at the edge of discovery is right here.